Okay, in this lecture video, we're going to start talking about the most abundant molecules on Earth. So we've already spent a long time talking about the molecules that are essentially the workhorses of the body. But now the most abundant molecules on Earth are actually fuel for the body, and those are carbohydrates. So carbohydrates are going to come from the light-powered combination of carbon dioxide and water, courtesy of our plant friends and some bacteria from their ability to do photosynthesis. And so they have a really simple formula, CH2ON, where N is some number greater than or equal to 3. So simple formula, but the simpler the formula, the more the molecules start looking alike. So we'll see that as we study some of their chemical structures. But we're going to talk about 3 major classes of sugar molecules. The first is the monosaccharides, and these are our simple sugars. So these are the units that are going to polymerize to make our more complex carbohydrates. So carbohydrates, just like proteins, are polymers of smaller units. So the simplest example of the monosaccharides is glucose. So the next class are the oligosaccharides. So these are going to be sugars where you've got about 2 to 20 units that have polymerized together. So they're the medium-sized complex carbohydrates. Probably one of the more common examples is sucrose. And then our third class that we're going to talk about are the polysaccharides. So this is where you've got more than 20 individual units that have now polymerized together. So common example of this complex carbohydrate would be starch. So overall, since you can get so many different combinations, just like with proteins, you get lots of different options for carbohydrates. However, since they have so few atom types and so few functional group types, they get to be very difficult to characterize. The samples of carbohydrates are very heterogeneous in terms of the order in which the sugars are attached, and there's no assays for function. So if you're looking at proteins, you could measure that protein's ability to bind a ligand or to catalyze a reaction in order to track it and purify it and study it. But with carbohydrates, you just can't do that. Doesn't mean they don't have function in the body, even functions besides that of fuel, but it does make them difficult to track. So we'll start with our simple monosaccharides as our first class that we're going to look at. And what you're going to see is that they are carbon chains with single bonds. So our simplest sugars then have 3 carbons. This first one that I'm going to draw is going to be glyceraldehyde. And you may have heard these 2 sugar words if you've studied anything about metabolism yet. If not, and you take 446 next semester, you're going to hear a lot about it. And the other simplest sugar will be dihydroxyacetone, which looks something like this. So this is dihydroxyacetone. One word, but when you're on an iPad mini, most one words are broken into 2. So we can classify our simple sugars, our monosaccharides, by looking to see whether or not they have an aldehyde functional group or whether or not that carbonyl is instead part of a ketone functional group. So that allows us to classify our sugars as either an aldose or a ketose. So it just depends on whether or not that carbonyl is part of an aldehyde or a ketone. Now, once you get bigger than 3 carbons, you start getting carbons that are attached to more than, well, I shouldn't say more, carbons that are attached to 4 different functional groups, which means we're going to have sugar molecules, monosaccharides, with multiple chiral centers, so carbons attached to 4 different substituents. And if you have a molecule like that, you start to have lots and lots of isomers. So again, another reason why carbohydrates are so difficult to study is because of the isomers present. So you get 2 to the n stereoisomers, where N equals the number of carbon atoms present. So that gets to be a lot real quick. So what we're going to have coming up are going to be 2 enantiomers, which if you remember all the way back to OChem, are non-superimposable mirror images. So we're going to be talking about D and L configurations. So configurations, not conformations, but configurations. Okay, so this means when you have 2 non-superimposable mirror images, all of the chiral centers in the molecule, all of the chiral carbons, have the opposite configuration between the 2 enantiomers. So we're going to need to first of all take a look at how we identify the chiral carbons and how we classify a sugar as D or L in terms of which enantiomer it is, because if it has multiple chiral carbons, we're going to have some systematic method. And the example we're going to use for that is fructose, which is a 6-carbon sugar. See if I can fit it on my iPad mini. 1, 2, 3, 4, 5, 6. Okay, so it also is a ketose, which means it has a ketone functional group. So now I got to add all my other parts here. So lots of hydroxyls and lots of hydrogens. All right, so here is fructose. And we can identify, first of all, the 4 chiral carbons in this molecule. So they are going to be 1, 2, 3. Oh, sorry, 3 chiral carbons in this molecule. Did I not draw enough? Hold on. Oh, no, I'm good. 3. So you notice the 2 carbons at the top, this one and this one, are only attached to 3 different functional groupings of atoms because each one of them is attached to 2 hydrogens. So those are not chiral carbons. So only the 3 that I have starred. So we could make a mirror image of this molecule. Here's my mirror plane. So the mirror image then would look like this. One, 2, 3, 4, 5, 6. Ah! There's a hydrogen up there. That's annoying. Let's see if I can get it on there. 1, 2, 3, 4, 5, 6. There. There we go. Okay. So to make our mirror image, it would look like this. Oh, got a hair on my iPad. So the way, since we've got 3 chiral carbons in fructose, we have to know which chiral carbon designates a molecule as being the left or the right enantiomer, the L or the D. And the one we use is the chiral carbon farthest from the carbonyl. So in that case, we're talking about this one. And the way you make the D versus L determination is that you put the carbonyl, you draw your line structure with the carbonyl here as close to the top of your page as possible. Find the chiral carbon farthest from the carbonyl, and then look to see if you have to go to the left or to the right to get to this OH group. So since we have to go right to get to the OH here, this is our D isomer of fructose, and over here then we have our L isomer of fructose. Now remember, in this case, in enantiomers, all of the chiral carbons are mirror imaged, right? So we have all of them have the opposite configuration in the D versus the L isomer. But that's not the only type of isomer you can have. You could have two sugar molecules where only one carbon center might be a mirror image. So in those cases, those two sugar molecules do not have their own name, or sorry, do not have D and L configurations in their name. Instead, they are completely different names. They have their own name, and they are diastereomers. So diastereomers are stereoisomers that are not mirror images. And in fact, if it turns out that the only difference between two sugar molecules is the configuration at one of the carbons, those two stereoisomers have a special name as long as it's not the D versus L. So those are called epimers. So two sugar molecules that have a complete mirror image, those are the enantiomers, and those are designated D versus L. Then you can have diastereomers, which have configurations about one or more carbon centers but are not mirror images. But if you only differ at one carbon, then instead of being D versus L, because it could be any of the carbon that are chiral, you have epimers. So let's take a look. So since my iPad mini is so tiny, I don't really have room to draw all the chemical structures, but you can look these up in your textbook and see for yourself. And if you can't see it, then I want you to come and see me about that. Oh, but before I draw these, let me go back so that I can give you some information about this. The one more thing that I want to tell you about looking at these sugar structures is, besides identifying the chiral carbon that designates D versus L, you have to know how to number these carbons so that we can talk about which carbons might be chiral centers, which carbons might have different configurations in two different sugar molecules. So you number them starting at the carbon closest to the carbonyl, and such that you can make the longest carbon chain possible. So in this case, it would be carbon 1, carbon 2, carbon 3, 4, 5, and 6. Okay, don't want to forget that part. So now, if you want to look at the structures of these molecules, I would do that and draw them in your notes and see if you can see why they're classified this way. Start with D-glucose. And you could draw its enantiomer by drawing a mirror plane. So that would be L-glucose. Then you could draw an epimer molecule of D-glucose. So that epimer molecule, so epimer, is D-mannose. So when you draw the chemical structure of D-mannose, you should find that at one of the other chiral carbons, it differs in configuration from D-glucose. Then you could draw an epimer of D-mannose, so another epimer, which is D-talose. And if you draw D-talose, you should find that it is in fact a diastereomer of D-glucose. So if you're looking to see at which carbons the differences happen at, D-talose differs from D-glucose at two carbons, carbons 2 and carbons 1, 2, 3, 4, 5, 6. So carbon 2 and carbon 3. D-mannose differs from D-glucose only at carbon 2. That's why it's an epimer. Oops, sorry, I realized I counted my carbons wrong. This is what I get when I'm holding my structures in front of me and trying to count without pointing. So carbons 2 and carbon's 4 for D-talose. And then, if you want to compare which carbocarbon is different between D-mannose and D-talose, look at carbon number 1, 2, 3, 4. Right? And then, of course, for the enantiomers, all carbocarbons have different configurations. So epimers only have one carbon with a different configuration. Diastereomers have more than one, but that's not a complete mirror image. That's non-superimposable. So those are some good structures to really take a look at.